we're now at a point of looking at these discrete variables to change up a little bit and say, let's consider now only really situations where you have a two outcomes really. So it could be a success or a fail, it could be a yes or a no, it could be a 1 or a 0, and what does that mean? Because we can do a lot of things with that. So these are called Bernoulli random variables, and the idea is that you have two outcomes. You assign one outcome as being a 1 value and the other outcome as being a 0. So often you think about it as being a success or a failure. Okay, and to start with, I don't know why I'm on that one. To start with, we think about what we've already been looking at in terms of values and outcomes. So if you have a look on the screen, you'll see over here is a table that you're sort of used to, where there's two possible outcomes. Your outcome could be 0 or 1. Okay, and because there are only two possible outcomes, we usually represent, or we will represent the 1 as being a success. We always think of that as being positive, so we're going to give them a value of 1. We're going to say the probability of that success, we're going to give a value of P. Therefore, the probability of the other thing happening, the failure, must be 1 take P. So that the two probabilities here add up to being 1 or 100%. Okay, so this is the mathematical way of writing one of these. It's basically just considering a single trial at this point of an experiment. So we're just going to flip a coin, and it would be 50-50 if flipping a coin and getting a tail is a success because you decided that's what you picked. Okay, the probability of getting a tail is 0.5. The probability of getting a failure, throwing a head, is going to be 1 take 0.5, which is 0.5. So there's nothing much too dramatic with it. Okay. The things to consider, because we're considering a lot of this stuff now, is what would be the mean result. So if we did it lots of times, what's the expected mean? Well, it's going to be whatever the probability of a success is. Why? Because the value that we're going to get, the probability is times by 1. Okay, the probability of a failure in that is times by 0, so it doesn't doesn't add up in that calculation. Okay, because it's 0 anyway. So it's just going to be 1 lot of P. So the mean is going to be P. 50% is the mean successes if you're tossing a coin, and tails is the success. Okay, we don't have to have 50-50. In fact, most of the time we won't have 50-50. The variance we're not going to worry about as such. We're just going to use the standard deviation. Okay, and so if you have a look at the standard deviation, you can, I'm not going to, but you can go back to the last little bit and look at the definition of how you calculate standard deviation, and it'll come out to be P lots of 1 take P. Okay, under the square root to make it standard deviation. The variance is P lots of 1 take P. But effectively, all you're doing is multiplying the two probabilities together. So if it's 50%, it'll be 0.5 times 0.5. Okay, if it was 70% as a success, then you would have 0.7 is P, and 1 take P is 0.3. So you'd have 0.7 times 0.3, and square root that. That's the standard deviation. We'll talk about that a little bit more in a sec. So, really quick example from the textbook. Okay, contrived type of thing. A pen is randomly selected from a box. 7 reds and 3 blues were in there. Let X equals 1, so the success is red, the failure is blue. Okay. Firstly, explain why it is a Bernoulli random variable. Okay. The reason we can say it is because there are only two possible values, 1 or 0, a success or a failure. Okay. And we have the probabilities of getting a success of 1 is 7 out of 10, because there are 7 red pens out of 10 total pens, and 3 out of 10 is the failure, 3 blue pens. And so therefore we can say it is a Bernoulli random variable. Okay, it only has two possible values, and the probability for success is 7 out of 10 or 0.7. What's the expected, what's the mean and standard deviation? The mean is just 7 out of 10. Okay, the standard deviation is 7 out of 10 times 3 out of 10, all under the square root, 0.458. Okay. Then just quickly a couple of questions that we can use to sort of show it. Firstly, are these going to be Bernoulli random variables? Well, if a coin is tossed, x equals 1 if the result is heads and x equals 0 if the result is tails, then yes, that's sort of the example we've been talking about. If two coins are tossed and x is equal to the number of heads tossed, that is not Bernoulli because there's more than one outcome that can happen. Sorry, there's more than two outcomes. You could get 0 heads, you could get 1 head, you could get 2 heads. 3 different outcomes are not a Bernoulli random variable. Okay, they are variables we've been talking about before. C, if you look at the spinner alongside, and x is the result when the spinner alongside is spun once. Yep, okay, it could be, but it depends on how you interpret the question. I think they're trying to say that, well, they are saying that x is the result. So they're saying x could be 1 or 2 because they're the results. All right, so in this one you would say it's not a Bernoulli random variable if you interpret it as being that, which is what they're saying, what it does mean. But you could do something very similar and say that getting a 1 is a success and getting a 2 is a failure, and assigning 1 to getting a 1 and a 0 to getting a 2, then it could be Bernoulli. But in this case, it's saying that the x is the result. So it's saying it's not a Bernoulli. A person enters the store, x equals 1 if the person purchases something, x equals 0 if otherwise. That is, you've got a success and a failure. And a letter of the alphabet is chosen at random, x is equal to the number of vowels chosen. Well, obviously, no. Okay, I think a letter of the alphabet is chosen, x is the number of vowels chosen. Well, when it says x is the number of vowels chosen, it's wrong. The second one actually asks us to calculate something pretty simple. Consider the spinner alongside, x equals 1 if the outcome is red and x equals 0 if the outcome is white. White's Bernoulli. Bernoulli because there are only two outcomes, x is equal to 1 and x is equal to 0. Okay. The probability of a success is 3/4. The probability of a failure is 1/4. Okay. So the mean for this is going to be 3/4. Okay, and the standard deviation is equal to the square root of 3/4 times by 1/4. Okay, now that's going to be important in a second. We'll have a look, and there's a reason why I picked that question 6 below. But you get a value there. What is it telling you? What does the standard deviation tell you? It's telling you how spread out is the data. If you did it lots and lots of times and collected every piece of data and graphed it, how spread out, how wide is that graph? How much values are there likely to be? What does that mean? It means that every single spin that you have, you get an outcome of 1 or 0. Okay, but if we were to consider it that if we did it lots and lots of times, on average, we should get 3/4. Okay, the standard deviation, when you consider it like this, seems a little bit meaningless. We're going to use that value though in the next little section. You'll see it sort of has more value on what it's all about. Okay, but I want you to think about question 6 here. It says, suppose that x is a Bernoulli random variable with a probability of success p. What it says is find the value of p such that, and this says the variance is maximised. Let's consider that as being the standard deviation because that's what we're doing in this course, but it's going to be the same reason. What probability is going to give us the greatest value that we would get for standard deviation? Remembering that standard deviation is the 1 take p is equal to this. What value of p That's an allowable value of p. Remember, every value of p is the probability. It has to be between 0 and 1. What's going to give us the biggest value of p times by 1 take p? If you think about the fact that I'm asking you this question, then there must be some sort of, like, it's not going to be some random, you know, it's 0.738. You know, it's not going to be something like that. Have a think about what happens when you start at a very, very, very low probability of something happening. So 0.001 as the probability. We're going to times 0.001 times by 1 take p, so almost timesing it by 1. Almost. Okay, but we're timesing it by 0.001. So it's pretty small. As we get closer to the probability being around about halfway, in fact, as we get to 0.5, we'll end up with 0.5 times by 0.5. Okay, which doesn't sound like very much. Okay, all right, but that is the highest value you can get when you do that, and you could graph it. You could see what a graph of that looks like. Okay, when p is between 0 and 1. So the highest standard deviation, the highest spread, is going to be when the probability of a success is half, is 0.5. Okay. Keep that in your mind for the next bit.